Log on, tune in, find out. Another good idea from Cambridge.
Tuesday session of the Newton Institute. I'm happy to announce then Wainer from the University of Leeds, who will give us a talk on predictably terminating, predictably terminating functions. Anyway, all the curtains, you will see.
One of them.
One of them.
Is this thing working okay?
Yep.
Right. I always feel with these things on, you need to do a song and dance or something.
Can you do something about the accent?
About the
Accent.
no. Well, I could try, I suppose. This is actually relatively old stuff, but I'd like to give it a plug, I suppose. Already in 1949, Turing clearly had it in mind that there was some potential for transfinite inductions as a method for proving termination of programs. And he wrote a note at the what then was called the Conference on the EDSAC Computer, which I believe, Martin Davis will correct me, but I believe was some product of Maurice Wilkes here in Cambridge, and there was a meeting that year at which Turing put forward a paper which the notes of which consisted of, I think, 3 pages. And it was essentially an analysis of a program for computing n factorial without use of a multiplier, because presumably that was pretty hard to do for those kind of computers, and the one he was working on in Manchester at the time. And he gave an analysis of how this program works, and also analysis of how it was clear that this thing terminated. So he was aware, at least, that transfinite inductions could be useful for termination. Actually, the example he gave used a very large ordinal, omega cubed, because essentially the argument was an induction on a certain lexicographic ordering on 3 variables. But he does mention the fact that he says explicitly that transfinite induction is a method which the mathematician accepts as good enough, if you believe in it, for determining termination of programs. Of course, it's good enough if all you want to know is termination, then knowing that a certain induction is available and will do the job is enough. But if you want to know more about the program, then it would be useful to know more about the proof theoretic strength, say, of that principle of induction, because then you would hope to be able to read off further complexity information of a mathematical kind in general on the program itself. And it's this idea that I want to try to follow through to a certain extent. So what I want to ask is, say, well, which inductions what are natural ones, and how could some of them at least be generated in a kind of predicative manner from below. Well, this area is to do with computations, programs in other words, which compute functions, and it's also to do with proofs, which prove theorems. In other words, it's to do with an intentional area of logic. So what we're going to be concerned with is an intentional notion of ordinal. So, first of all, I'm going to try to describe what I would mean anyway by an ordinal presentation. So, a presentation of a countable ordinal is nothing other than a given counting of it. By which I mean the ordinal alpha is presented by giving an enumeration of finite subsets of it, nested so that they increase and then the ordinal itself will be just the directed union of such an enumeration.
So these have a Neumann origin.
Yep. Yeah. In addition, we make a requirement which won't play any explicit role in this lecture, but it's important to do so. Firstly, so it's just about how predecessor and successor, immediate successor, react together with this enumeration. So one would normally require also that if beta already appears at stage n, then beta plus 1 will appear already at least at the very next stage, and secondly that if beta plus 1 belongs to alpha n, then its immediate predecessor is already there in alpha n. So in other words, each stage is closed under immediate predecessor, and there is this kind of closure property about successor, which gives you a lot of added, actually quite a lot of added useful structure. Now the point is here that there is a very natural and very simple functor associated with this picture. Which I shall call the rank functor. And I'll denote it by G alpha. And it is going to be a functor from the most trivial category of natural numbers, in which there is just one arrow between n and n plus 1, namely the embedding of n into n plus 1, and the category of all natural numbers in which arbitrary, finite, strictly increasing maps between one number and a greater one are allowed. Okay? So, keeping this picture in mind, first of all, G alpha on n is going to be simply the size of alpha of the nth approximation, and G alpha on the embedding from n into a greater number m is obtained as follows. First of all, take a number less than G alpha on n. Okay? Well, call it k. Take the kth element of alpha n, call it beta, and then shift up to the nth approximation. Beta will appear there, but at a much higher level, because other things will have got squashed in below it as the enumeration proceeds. So in other words, I could describe that in the following way. Okay, take k, take the kth element of alpha n, that's beta, and do g beta on m. Okay, so the picture is this. At stage n, the elements in alpha n are enumerated. At stage m, the similar kind of thing happens. We know that each thing that occurs here will crop up at this stage, but of course many other things might crop below it which didn't appear at stage n, and in the limit, beta is going to be addressed at the end of the arrow. Okay? In other words, alpha, together with its presentation, is the direct limit of this functor, and I shall regard G alpha as being the kind of canonical recognition of the structure alpha. Notice it doesn't tell you very much about any transfinite inductions about alpha, only that each alpha n exists. But it's a beginnings, and it's a kind of sign that you've got some information about alpha. You've somehow got alpha, and the idea behind our autonomy condition, which is going to occur on the next board, is that given G alpha, a recognition of alpha, then we shall allow ourselves to do alpha recursions, and we'll see how far that autonomy condition would take us. A note, first of all, which can go here. A natural transformation between one G alpha, I shall write it this way, and another one is in this context an order-preserving map pi from alpha into alpha dashed, such that, in addition, it restricts at each n. In other words, pi restricted to alpha square bracket n takes you into alpha dashed square bracket n. Okay? Now this ensures that G alpha will be bounded by G alpha dash, and furthermore, for most, and certainly those we shall consider most kind of notation systems that crop up, it will also ensure that G alpha is, say, elementary recursive in G alpha dashed. Okay? So natural transformation gives you comparability, which you wouldn't have if all you had was an order-preserving map between alpha and alpha dash, because the alpha presentation might grow very quickly, whereas the alpha dash presentation might grow very slowly. Okay? So there is although we don't know what a natural ordinal is, we do have a good notion of a natural partial ordering on them. Right, what am I up to? How are we doing for time? Fine. Okay. So now, predictable termination. So the idea, it's fairly obvious now what I'm going to try to mess about with. So the notion of predictable termination is as follows. You are given something simple. It might be 0, it might be omega. I don't really care. Either of those would work perfectly well, but I'll choose omega. And I'll give omega the following presentation. Okay, in other words, omega is just essentially going to be the identity function. The process is this. If G alpha is already previously defined, then allow alpha recursions. You see, given you got this presentation up here, you have enough information to be able to define what you mean by recursion. Okay? So that's going to be our principle. As I said before, it is not the case that having G alpha already ensures that you know all about alpha induction. Okay? But it's a way of saying, well, at least I can see this ordinal, and now I'll allow you to use it. Okay? That's the principle. Now, what we could do with, since I've said allow alpha recursions, what we could do with is some kind of normal form for alpha recursions to compare everything with. It just makes life easier. So, I'll take this definition, okay, a version of what's often called the fast-growing hierarchy. So B alpha is a number-theoretic function, which in those cases where we will be interested in it, it will actually extend to a functor in the sense I've described. B alpha is going to be just the successor function if alpha is 0, and if alpha is a successor, it's the successor function on natural numbers if alpha is 0. If alpha is a successor, then B alpha is just going to be the result of composing B beta with itself. Doesn't matter whether you take double composition, triple computation, or even variable n times composition. It doesn't make a lot of difference because actually, as it turns out, we're dealing with rather big functions here. So then if alpha is a limit, then B alpha is going to diagonalize over the B alpha n's. So alpha is given to you as a sup of alpha 0, alpha 1, alpha 2, alpha n, and so on. So we'll just take the diagonal in that case. Okay? These are good enough. All we need to be sure of is that alpha recursions may be easily reduced to B alpha prime for alpha primes roundabout alpha. I don't care if alpha prime is omega times alpha, for example. Okay? For alpha prime near to alpha. And that's what I mean by giving us a suitable normal form for recursions. And here's how the principle works. So I'm giving you omega. Okay? So that says I'll allow you to make omega recursions. I'll allow you to do primitive recursions. With primitive recursions, we can see and define b omega. Okay? Now it turns out that b omega is a rank functor, okay, for a certain ordinal. Which I shall call Tor1, and Tor1 is indeed bigger than omega. So from omega, with recursions, we can see Tor1. And that's enough to suggest what's going to happen next. With Tor1, we're able to do Tor1 recursions. B Tor1 will again be a rank functor for a certain ordinal Tor2. Etc. And Tor will denote the limit of Tor0 and so on. As I said, it doesn't make a lot of difference where you start with Tor0. It could have been 0, but it works a little bit more smoothly if I choose omega. Okay? So the question is, what are these Tors? So the accessible recursive functions are those computable with resource bounds be alpha, where alpha is less than Tor. Okay? Because of this normal form up here, you see, this Tor really will be a limit of this process, because anything I can define just below Tor is still going to be kept below Tor, because what I said about these B alpha functions, they're enough to give you all kinds of recursions. Okay, so there will be that closure point. So what else do I need to say? Right, and this class equals those functions which can be proved to be computable or recursive in pi11 CA0. And the reason is that Tor at level n is exactly the proof theoretical ordinal of the system of inductive definitions iterated n minus 2 times. So for example, Tor0 is omega. Tor1 is very disappointing. Tor1 is really just another representation for the ordinal omega times 2. But Tor2 is the ordinal of P on arithmetic, epsilon 0. Tor3 up here is the Howard ordinal. the ordinal of one uniterated inductive definition, and so it goes on. So, since this theory is, for arithmetical sentences, at least conservative over all finitely iterated inductive definitions, our result is obtained in this way. What else should I say? I've not said anything about the technicalities, and you can always find those in our book with Helmut. What I would like to say is that it seems to me that one could, at this stage, say that those ordinals which have presentations which can be naturally transformed into anything along this scale should be considered as being natural, to go back to something we were talking about a week ago. Of course, there may be lots of other stuff which would count as being in some sense natural, but this is a kind of stopping off point where one obtains a closure with respect to this kind of predicative autonomy condition up here. Now, that of course is a debatable bit, why that one, why not another one? Is it reasonable? Well, it seems to me it's reasonably reasonable. So I'll stop there.
Thanks. Comments or questions?
What were the resources? You said it's with resource bounds. What
Yeah, well, when you're talking about such big functions, it doesn't matter whether you count time, space,
So
whatever.
Any reasonable.
Yeah, anything you like. Yeah. This is mathematical complexity. It's not computational complexity.
You described the G alphas as functors. So does that mean that the B alphas are also functors?
Yes, those B alphas, for certain well-behaved alphas, and these all are, the B alpha will be a functor from the category n into n. And when it's restricted to n0, will be identical to the G.
So there's a natural definition of the diagonal operation on functors.
Yes, it would take some time to unravel from the definitions. How natural that is. I think so, yes, but the other thing I should have said is that this idea of using functors in this area to do with notations goes back to Peter originally, but was also taken up by Girard, and what we're saying here, we're talking about the very, very beginnings of what Girard called pi-1-2 logic, but this is the context here is quite different, and the methods are too.
Okay, last question.
Just some simple syntactic questions. What do you mean by beta element of alpha of n? And what do you mean by the size of alpha of n?
Right. These alpha n's, by accounting, I did say, I think, Tony, I hope I said, but I didn't write it down. By accounting, I mean an approximation by finite subsets. So each alpha n is finite. It's a finite subordering of the ordinal alpha.
In what sense?
In what sense? Finite.
I think I don't understand what you mean by this approximation.
So any
do you go from
any
alpha
structure
of
can be approximated as a directed union of its finite substructures, essentially. So here we're just applying it to an ordinal. So each alpha n is a finite subset of the whole set of ordinals alpha itself. Just an ordinal. set
Maybe we need to
theoretically.
discuss it offline.
I'm sorry?
Maybe we need to discuss it offline.
Right, and by the G alpha here, I mean just take the size of alpha n. How big is that finite set?
Okay, I think we should close. Thank the speaker again.